This is video 13. In this video we present the different kinds of cut of the grid that will be used along the proof. There are 5 parts in this video. First, we will cut the grid by using a finite cycle. A cycle is a path such that its first position is equal to its last position. We consider simple cycle. The cycle intersects with itself only at its first and last position. This finite path can be extended into a B-infinite path by computing the indices modulo the size of the cycle. This B-infinite path can be used as a window. Note that this window is not simple, but it is possible to extend the definition of the right and left side for such a B-infinite path. The Jordan curve theorem can be used to show that the grid can be cut into 2 graphs by this window. Moreover, one of this graph is finite while the other one is infinite. In this case, the graph G2 is finite. The graph G2 is also the right side of the window. Here is the graph G1. This graph is infinite and is the left side of the window. Now, we cut the grid by using discrete lines. First, consider a vector v. Here the coordinate of the vector v is 5, 3. Now, consider the continuous line of slope v. We would like to cut the grid using this line. Since we consider a discrete setting, then we need to discretize this line. To achieve this goal, consider the following function h. This function is called the height function and is used to compute the height of a position. In this example, we represent the height of some positions. Consider a position u, then translating this position by 1, 0 decreases the height by 3, translating the position u by 0, 1 increases the height by 5. Also note that the height of u is the same height than the height of u translated by v. Finally, note that the height depends on the vector v. The only argument of h is a position of the grid, since there will be no ambiguities along the article on which vector v is used to compute the height. Now let P be equal to the abscissa of V plus the ordinate of V. In this example, P is equal to 8. In this example, consider all the positions of height between 0 and P minus 1. These positions are in gray. They form a B-infinite line which can be used as a cut of the grid. Remark that this window is periodic of period P, and thus the translation of this window by V is identical to itself. Here is the left side of the window which contains all the positions of height more than 0. Here is the right side of the window which contains all the positions of height less than 7. Now we will cut the grid by using the extension of a good path. This kind of cut of the grid is a generalization of the previous one. Consider a good path P. The direction of P is the vector v. We consider the height function associated to v. By extending the path P, we obtain a simple B-infinite path which can be used as a window. This window is periodic and the length of this period is the length of the path P minus 1. Now consider the maximum and minimum height of the path P. Then all position of the window have an height between these two values. We represent here the right side of the window. All the positions of height less than the minimum height of P belong to this graph. We represent here the left side of the window. All the positions of height more than the maximum height of P belong to this graph. It is possible to make several combinations of these cuts, but we present a specific kinds of combination using the visibility of the extremities of a finite path. This notion of visibility will be important later. Consider a finite path P. The extremity P1 is visible from the west. In other words, no position of the path has the same ordinate than P1 and a strictly lower abscissa than the one of P1. Similarly, the last tile of P is visible from the east. Then it is possible to extend the path P into a simple B-infinite path as shown in this figure. This B-infinite path can be used as a window. Here is the left side of the window. Here is the right side of the window. Sometimes we have to deal with 2 cuts of the grid at the same time. We explain here how to deal with this problem. Consider a first cut of the grid. The graph G1 is the left side of this cut. Here is a second cut of the grid. The graph G3 is the left side of this cut. Now consider the intersection of G1 and G3. This graph is connected. In this simple case, making the intersection of two graphs is a correct solution. Now we will consider a more complex case. Consider a third cut of the grid. The graph G5 is the left side of the cut of the grid. Now, we consider the first cut of the grid and the third one at the same time. Here the intersection between the graph G1 and the graph G5 is not connected, thus we need a better way to consider two cuts of the grid at the same time. Consider the first cut of the grid and its window W. We chose a position of this window as W0. Now we consider a good path Q such that Q0 is W0, the direction of Q is V. Consider the extension of Q into an infinite path in the direction V. Suppose that this infinite path intersect with W only at position W0. Now, we can consider the window which is the concatenation of the segment of W from -infinity to 0 with the extension of Q. The new window is W'. Its left side is a graph called G1-. The graph G1- contains the left side of the extension of Q. Moreover, this graph is a subgraph of G1. Similarly, we can define another window which is the concatenation of the extension of Q in the segment of W from 0 to +infinity. The new window is called W2. Its right side is a graph called G1+. The graph G1+ contains the right side of the extension of Q. Moreover, this graph is a subgraph of G1. Remark that the union of G1+ and G1- is G1. We say that we have split G1 into G1- and G1+. We have applied our definition of the cut of the grid to the graph G1.